All right, here we go, continuing with hypothesis testing and kind of the basic introduction. So we're going to talk about point estimates and parameters. Now, this is exactly the same thing that we discussed in terms of confidence intervals, but it's definitely worth mentioning again. So for point estimates, we have X bars, and X bars are going to be telling us about the parameter mu, right? The sample mean tells us about the population mean. We also have p hats that tell us about the population proportion. So sample proportion telling us about a population proportion. And we have s squareds, which tell us about sigma squareds. So sample mean telling us about the population mean. Sample proportion telling us about the population proportion. Sample variance telling us about the population variance. Now, even though it's not the standard deviation that we refer to, the standard deviation does tell us about the population standard deviation. So those work. So what we really need is these point estimates distribution in order to do hypothesis testing. Now, as long as we can make the normality assumption, and the normality assumption is either that we know the original values of the random variable are normally distributed, or we have n being greater than 30, then we can rely on the central limit theorem. But we have two choices of how x bar gets distributed. If sigma is a known entity, which that's not a real popular thing to have happen in the real world. How many times do you really know the population standard deviation? Well, not really a whole lot. There are instances, but it's not very often. And when we do know that standard deviation, then the distribution is normally distributed with a mean of the population mean and a standard deviation, or a standard error is what we call it, of sigma divided by the square root of n. Now, if sigma is unknown, then the x bars, they follow a slightly different standard sampling distribution, and that is the t distribution. Now the t distribution has degrees of freedom. It has an n-1 degrees of freedom, and remember it has also, it's telling us about the mean of the population, and the mean of the population with a standard error of s divided by the square root of n. So that's where it differs from the normal. Now the p-hats, they're always distributed normally with a mean of p and a standard error of the square root of pq divided by n. And we're going to learn that this p and this q, unlike when we had confidence intervals, these are going to be underneath our null hypothesis. Now the s squareds, if you recall from when we did confidence intervals on these, the s squareds are distributed with this distribution known as the chi-squared distribution that looks like that. So these are the ways that we're going to find out what value here, not the test statistic, but our test statistic will fall into one of these distributions, but our critical value will be based upon one of these distributions, which tells us where this critical region, or where this rejection region will begin. And so the way that these things link is that this will be my rejection region, and one of these distributions will tell me about how I will find where this place starts, where this rejection region starts. And we will use inverse distributions in order to get to this. So this would be an inverse t, or an inverse normal, or an inverse chi-squared. And that is in order to get us to find where that critical value actually is. Now, the inverse t is just, if you're using tables, it's just using a t-table. The inverse normal, you can find the inverse normal at the very bottom row of any t-table, or you can look in the body of the normal table. The inverse chi-squared, that again is just a table, because those two distributions, the inverse t and the inverse chi-squared, our most popular methods of using those are actually as inverse distributions. So the tables are automatically set up just to tell us what those values are. All right, now once we have the critical region well defined and we found a critical value, okay, so let me go ahead and highlight that again too. This will be what we say is the critical value right here. CV stands for critical value. So once we get that critical value in place, then we'll be able to do our test. But this critical value is not only dependent upon just the distribution, so it's dependent upon number one, the distribution of the distribution of the parameter, right? So the sampling distribution. But it's also dependent upon something called the confidence level, indirectly. And this confidence level, we set that up not because of how sure we actually want to be, but we want to set it up based upon something that we'll talk about a little later called a type 1 error. So the confidence level, called a CL, this is something that we heard talked about in terms of a confidence interval, and it still means the same thing. It's 1 minus alpha. That's the confidence level. But we actually are more concerned with alpha, and this is called the probability of a type 1 error. And we'll discuss what a type 1 error is later. But it is important, even though we don't need to know exactly what it is. It's important that we understand it, not a type 2, a type 1 error. It's important that we understand this type 1 error because it shows us that you can't just set alpha to be really anything under the sun so that we can get greater and greater levels of confidence. We have a balance to maintain there. So when we do this confidence, or this critical value, we're going to have for our one-tail test over here, this is your confidence level, CL is confidence level, and then over here is your alpha, your 1 minus your confidence level. And that will help us to tell what our value is for our critical value. So if this were an inverse normal, which is what it is because we're looking at p's, right, this would be point and then whatever we have. And our alpha we've set up to be a 0.01. And so we would do an inverse normal of 0.01. And this is going to give us what our z value is equal to. And we'll call this a z of 0.01. Now, when you do it this way, put in 0.01, your calculator, if you look in your calculator, is going to give you a negative value. That's because 0.01 is actually over here, because your calculator always tells you what's in the left tail. However, we want what's in the right tail, so we'll just change the sign to a positive value. So when we have done that, that's what we want to do. We want to find out what that value is. So you probably should try that in your calculator right now. Put in this value right here, 0.01, into the inverse normal distribution, and let's find out what that z is. So this is going to give us a 99% confidence level, right? This is 0.01, not 0.1. Students make a mistake with that quite often. And with that 0.01, then we can find out our value. Okay, I pulled up the table here so we can look it up in the table. Now doing it in the calculator is even easier. So I'm looking at a one-tail area here. Remember, a t-table does tell us about z's if we look at the large degrees of freedom or infinite degrees of freedom. So I'm looking at 0.01 here, and so I'm going to be looking down here, and I'm going to go all the way to the bottom of this in the second column from the right in order to get that. So see a large degrees of freedom, which is actually a z, and here is my value for my z. So this is 2.326, and that is my z value. So that is my confidence level, or excuse me, my critical value based upon a 99% confidence level. So this is critical value. And that critical value I abbreviate with a CV, and that CV is based upon this confidence level. Now it's important that you understand that the confidence level in a hypothesis test does not indicate the same z-score as a confidence level for a confidence interval. So be careful of that because one and two tail tests give you different values there. That's why those tables have one tail versus two tail. All right, the next thing that we want to talk about is this type 1 and type 2 error. Now the type 1 error, that's what alpha is. Alpha is the probability of committing a type 1 error. So a type 1 error, that is the probability that we will reject the null and accept the alternative when the null hypothesis is actually true. So what that means is that we will actually support our claim when it's actually what was going on before. So in terms of us, we have the manufacturer saying now that we've accepted the alternative, right? We've said, okay, our claim is good. So we've said the claim is good when the new medicine is not better and the old actually is better. So for us, a type 1 error is claim that the new has a better success rate than the old when, and here's the problem, the old is actually better. So the old is better. So what's wrong with that? Well, let's just think about this medicine. So let's say this medicine is something that cures a disease that will kill you. So we have now said this new medicine is going to cure you more often than the old medicine. So now we start prescribing this to people, and more people are going to die than they did when they were taking the old medicine. We just did a great disservice to people. We killed them off, basically. And that's not good, right? So we want to avoid making that type of error as much as possible. Notice how small the alpha has been set. There's only a 1% chance that we will make this mistake of claiming that the new one has a better success rate than the old when the old is actually better. We'll only make that 1% of all the times. And when I put that kind of a life-death urgency to this, it makes it even clearer. Now, there are 4 different scenarios that happen here, and that's what this little table tells you about. So we were just talking about the type 1 error. So this says that the null was true, and we rejected the null. So when you reject the null, you accept the alternative, you accept the claim. So when the claim or the null was actually true, that's our type 1. Now, if the null was false, and you rejected the null, then you made a correct decision, right? And then if the null was true and you failed to reject the null, then you made a correct decision. And here's the other error that we can make is a type 2 error. This is you fail to reject the null, but the null was actually false. In other words, the new medicine was actually better. Now, this isn't as severe of an error because you're not going to hurt as many people. Yes, you could have helped people, but you're not going to inadvertently hurt people. So that's why this one is not as severe. And a type 2 error just comes along for the ride. So we're not controlling that one. And its probability, by the way, is called beta. All right, so that's going to end it for right now. And then we're going to come back and we're going to talk about these for some more